on. The second case is the free damp motion, still free of the external force, but it has the damping force effect to the system. Okay, so for the free, that means the right hand side is zero, still homogeneous, and with the damping force involving, so going to have the middle term or the term involving the velocity with the damping force effect to the spring. So the typical equation is m x upper prime plus beta x prime plus k times x. K is a spring constant, m as a mass as we saw in the earlier case, and the beta now is the new number, is the damping constant. Okay, it is the factor to the to the to the velocity. Actually, not the power. This is supposed to be the factor. The factor of the velocity. Okay. So with this form, you can rearrange it to see like the general pattern as you look for the characteristic equation. Oh no, it's called the auxiliary equation, and the m's as the solutions of those auxiliary equation. Well, I would not be focused more on the lambda case for the free damp motion. Just stick with the general pattern, and when you get the numbers, replace it into the equation. It will come along. It will come along. And with the form that we have three terms, recall when you solve the quadratic equation of the auxiliary equation, you're going to have three cases of the solution. Depends on the discriminant. Okay, actually these two numbers, these two terms, they are from the use of the quadratic formula, the minus b plus minus square root of b square minus 4ac divided by 2a. Okay, so stick with the form in general, and then when you get the solutions of the auxiliary equation, it will tell you what the solution gonna be. So this in the table here, just a summary of the three cases of the solution. Okay, the three cases, how how the solution of the free damp motion gonna be case one, or the case is the two solution. Let me go here. As a solution form, you see the m as a negative lambda plus square root or minus square root. So that in this case, you have the two distinct real roots. Okay, two distinct real roots. See, the solution is the e to the power everywhere. And this case is called overdamped because the exponential part, which is a negative sign, it decay rapidly. Okay, if you recall the nature of the exponential with the negative sign, it decays rapidly. So it's called overdamped because both terms of the solutions, they have the exponential involved with the negative sign. Or it could be negative and positive, but it's gonna affect to the motion of the the mass attached to the spring until it down to the equilibrium position. And then the other case is called critically damped. That means the case that you have the repeated root, repeated root, or case two. Okay, the exponential term, and then another term, you have the same power of the exponential, but you have to multiply by the independent variable. In this case, it's the t or the time t. So that means you can have like another factor involving into another term of solution. That's why it's called the critically damped. So it's going to be fast, okay, fast, but it's not like totally decay. It's going to be the algebraic term to represent the motion that just slightly different from totally decay. Okay, and the last case, the underdamped in the case that you have the conjugate complex solution or the square root of the negative number. So in that case, it has sine cosine involved. So for the free damp motion, you're going to have both exponential and the trig term as part of the solution for the underdamped. That means the the motion going to be oscillating, and then finally it damped down to the equilibrium position. Okay, so it's like oscillate real fast and then go to the zero. Okay, so exponential term here is a damping force or damping fact, not the force, damping factor that's going to affect majority of the graph. So going to force it to go down to equilibrium very quick. Okay, the x prime equals zero. That means that is the maximum minimum point of the position. Okay, I'm gonna help you set up the equation real quick and then do the cheating way again to give you the solution and analyze the graph. So let me let's do the key term again. We have 8 pounds stretching 2 feet. So this part gives you the spring constant. Damping force, so that's the thing that tells you they have the middle term or the beta times the velocity. And usually it already tell you like it's 2 times the instantaneous velocity. Just analyze just the key term, bring it into the formula. We're gonna find the equation of it should be the equation of the motion initially released from the equilibrium position with equilibrium position, upward velocity. All right, each one. So the first part, again, tell you about the K. And the, that's the force. Stretch 2 feet, so F equals Kx. That means 8 equals K times 2. Therefore, the K is 4. I like 4 a lot. There are a lot of 4K involving here. So K is 4. And then it's not removed. So we use the same mass there, the same 8 pounds. So the mass, which is the 8 pounds divided by 32, which is 1 over 4. Okay, then this is the weight. This is the weight. M is 1 over 4. What else that we know? The damping force 2 times. That means the beta is 2. Okay. Act on the spring, determine the equation of the motion initially released from equilibrium position. So that means x at 0 equals 0, equilibrium position. Upward opposite direction. So that means x prime at 0, upward negative sign, 3 feet per second. Okay. So the equation of motion is the m x double prime plus beta x prime plus k times x no external force. The m is 1 over 4 x double prime. The beta is 2 x prime. The k is 4 times x equals 0 with these two initial conditions. Clean up the equation, multiply all by 4. Going to be x double prime plus 8x prime plus 16 times x equals 0. And then use the auxiliary equation. Put a note here. The auxiliary equation would be, again, they are not the same m, okay? Just m notation that we used in the past. 8m plus 16 equals 0. Looks like we have the double root here, right? That's the perfect square. So m plus 4 times m plus 4. So we get repeated roots, negative 4, negative 4. As you see, like the numbers here, they all are positive, positive. You're gonna get m in the negative sign as one of the observation. If m is a negative sign, you have exponential decay. So that's why it's from the damping force. They force it to go to the equilibrium point. So m is negative 4 and positive 4. Therefore, the position equation gonna be x as t equals c1 e to the negative 4t plus c2 e to the negative 4t, but we make it linearly independent, so multiply by another independent variable t. Okay. From using the x at 0 equals 0, x prime at 0 equals negative 3. So we get like a 0 is a quick one. So this is C1. Oh, that's nice. C1 is 0. So this term is gone. So then for the x prime, I'm going to cheat again. So C1 is 0. So C2 going to be negative 3 because it's based on the derivative. As if our derivative, since C1 is gone, so you don't have to worry about C1. So it's pretty much like based on the C2 term. So we get two numbers, C1 and C2. Therefore, the equation of the motion is x at t equals negative 3 times t e to the negative 4t. Okay. And the graph looks like this. So this is the second case, which is called the critically damped. So with the effect of the t that multiply on top of the exponential decay. All right. So what else that we have to find? Vitamin, not that's it. Yep. So if they ask for the maximum height, that means you're gonna find the x prime, phi t at x prime equals 0, and that should be somewhere over there. Okay. And the graph below that means this is above the equilibrium position. So it's bounce up and then go down back to the equilibrium position.